Okay, this is Physics 1A for May 24th, and today we're going to be talking about gravity. We've talked about gravity before in this class, but we really only talked about kind of like just normal gravity, I guess you might say. Gravity where gravity is just 9.8 meters per second squared, it's always the same, right? But we'd like to talk about gravity on a larger scale, such as the gravity between the sun and all the planets, or the gravitational attraction between different stars, that kind of thing. So that's what we're going to be discussing today. And the way that we're going to do this is we're going to start off talking about astronomy, working from kind of the ancient Greeks up through Copernicus, and then we'll transition into talking about Kepler's laws that describe planetary motion. And then from there, we're going to go into our modern understanding, well, our modern classical understanding of gravity from Newton, and then we're going to move into gravitational potential energy. So that's our kind of plan for today. All right. Okay, so let's talk about astronomy first. So astronomy is one of the kind of oldest of the sciences that we have. It's one of the most precise sciences that we have from the ancient civilizations. And that's because these civilizations would take really detailed astronomical data. They would plot the location of stars throughout the year. They obviously, that they named lots of constellations that to this day we still have, kind of names for. And they noticed certain things. Like, for example, they noticed there's, if you look up at the night sky at nighttime, you'll notice that there's one star that basically doesn't move, and all the other stars circle around it. That star is called the North Star, and it's a star that we can use to basically kind of guide our way at nighttime because it always points north. So they start to notice that there's patterns with the way that the stars move, and they start to kind of come up with a system to describe what they see, right? And that system is now referred to as kind of like the geocentric system. And it was largely developed, or at least kind of written down, by a guy named Ptolemy in a book that you can still buy today called the Almagest, where what Ptolemy did was he basically described kind of a system of the world. I don't think he would have used the word universe, but the system of the world, which included Earth, the Sun, the 5 inner planets, so that's Mercury, Venus, Mars, Saturn, and Jupiter. Those are the planets that the ancients knew about. And Ptolemy's goal was basically to be able to kind of predict where each of these things was going to be on a day-to-day basis. And I'm just going to kind of give you a brief history of what Ptolemy's system looked like. So Ptolemy's system looked something like this. He had the Earth sitting here in the center. Okay, so that's us. Whether I don't know if you all knew this or not, but I grew up going to school, and somehow my teachers led me to believe, or maybe I just incorrectly believed, that ancient civilizations used to think the Earth was flat. Is that something that you all believe? That, like the ancient Egyptians, the Greeks, ancient Chinese civilizations, that the Earth was flat? Is that how you all grew up learning things, or was it just me? Yeah? Okay. The truth of the matter is they all knew the Earth was round. And the first calculation of the radius and the circumference of the Earth was, at least that we know about in the West, was done in ancient Egypt a long time ago. Okay, so they knew the Earth was round. There's a lot of reasons why they knew the Earth was round, and Ptolemy actually explains them at the beginning of his book. Okay, so one of the things he talks about is that if you watch ships coming in from port, like you're sitting in a port city and you watch big ships come in, that you'll always see the mast of the ship before you see the bottom of the ship. Like as the ship kind of approaches on the horizon, you're going to see the top of the ship before the bottom of the ship. That was one of their arguments. The other argument was that if you place a pole in the ground and you look at the shadow that's made by that pole at a certain time of day, like let's say noon or something like that, and then you go to a different location that's maybe 100 miles away and you do the exact same thing, the shadow is going to look different. And the angle between like the shadow and the pole can be used to basically describe your latitude, your how far you are away from the equator. So there are lots of different reasons why they believed the Earth was round. That doesn't mean that like average people thought the Earth was round. Just like today, there are probably tons of people that didn't think the Earth was round, but people that worked on astronomy thought the Earth was round, basically. People that were mathematicians and scientists. Okay, so Ptolemy thought the Earth was at the center, and I mentioned that there was this star called the North Star, and it's right up here at the top, directly above the North Pole of the Earth. So if the North Pole of the Earth is here, then the North Star is basically right here. And then he had the idea that the Earth was basically surrounded by a sphere of what are called fixed stars. So let's draw a sphere here. Put the Earth in the center as best I can. Make it a little bit smaller. So here's the Earth in the center, and then here's this sphere. It was called, I don't know if I need to write it down. He called this the sphere of fixed stars, and he believed that painted on this sphere were tons of little points of light. He didn't say anything about how far away these things were. He just said that you had what was called a sphere of fixed stars. Okay, and he called them fixed stars because they were fixed relative to each other, which is why we can look up in the night sky even today and work out constellations that have looked pretty much the same for thousands of years. So, the distance between these stars here was the same, and the distance between these stars here was the same, and you might have some other stars in here all throughout this sphere. Okay, but the idea was that all the stars were on the surface of the sphere. Okay. There weren't any stars on the inside. All the stars are on the surface of the sphere. And the distances between the stars were fixed. That's why he called them fixed stars. Okay. And then in order to... So this might be like a constellation down here, right? Where you have three stars some distance away from each other. And then he said, okay, this entire object basically rotates around in a circle. Probably like this. Okay. So the entire sphere, once every single day, would rotate around through 360 degrees. Will the constellations ever change? I mean, so it's possible that some of the stars in the constellations could burn out because stars don't last forever. And otherwise, they probably shouldn't really change. I'm not an astronomer, but does anyone else know anything about that? Maybe somebody in here is studying astronomy and maybe knows a better answer. I'm pretty sure that they're pretty much going to stay the same. There's going to be little small changes here and there, but stars live for a really long time. So anyway, so the idea was that this happened once every day, one time per day. You go through one rotation, and this will produce most of the way you see stars. You know, if you go look up at the night sky at nighttime, you can observe this happening. You can watch, you can go outside at nighttime. You can look at where the Big Dipper is. You can locate the North Star. So notice where it is, and then if you wait like an hour or so, you'll notice the Big Dipper has basically rotated as if it was like on an arm that's basically rotating throughout the night. And it's rotating around, it's rotating around the North Star, basically. Okay, so that was his explanation of the motion of the stars on a daily basis, right? And he thought that the Earth was still at the center, okay? So there's no rotation of the Earth. Nowadays, we know that there is no sphere of fixed stars. The stars basically just go on forever, and it's actually the Earth that's rotating on its axis that produces this motion, right? Would you all agree with that? And then the other question would be, is it clear to you that saying the Earth rotates, or saying that the Earth is still, but there is a sphere that rotates around the Earth, would you all agree that they're basically going to produce the exact same observation? You really can't tell the difference since we're on Earth. We can't tell if the Earth's moving. We're on Earth, right? But they should produce the exact same appearances, right? This is all Ptolemy cared about. He just cared about, can I produce a system that will explain what happens on a day-to-day basis, right? And he didn't care if that meant the Earth moved or if it meant that things moved around the Earth. It did not matter, because to him, they both give the same appearance, right? Okay, now this is the sphere of fixed stars, but there are other things that we have to deal with, and those are the things that actually create a lot of problems for Ptolemy. So the other things that we have to put into here are the sun and the planets. So we've covered all the stars, which is a lot of stuff, but we're left with the sun and the planets that we have to explain too, right? So what Ptolemy did was he said that the sun travels along another path. So I'm going to draw another path in here, and it's going to be kind of like this. This is a circular path that goes around the Earth. And this thing is called, we still use this name in astronomy today, we call this the ecliptic. And this is where the sun resides. So I'm going to use green for the sun. So the sun, here I'll put it like right here. So here's the sun. So the Earth is in the center, and here's the sun. And what the sun does is it goes backwards on the ecliptic. So if the stars are rotating in this direction, the sun is going to rotate in the opposite direction. Okay, so the sun moves along the ecliptic. Now the sun is going to take 1 year to go through that path. So it's going to go this way down to here, and then it's going to rotate back around until it gets to here, and then it's going to be going this way, and it's going to take 1 year. Every year it's going to go around this path one time. So it takes 365 and 1/4 days, exactly the number of days in a year, to complete the path of the elliptic or whatever, to complete one orbit. I guess you'd call it an orbit. I don't know. Okay, so this is his system to describe what the sun does. So what does the sun do that he has to describe? Well, first of all, in the summertime, the days are longer, right? And in the wintertime, the days are shorter. And there's also these specific dates when you have equal amounts of night and equal amounts of day that occur here and here on the opposite side. Okay? This is called an equinox. So it happens there's the vernal equinox, and it happens in spring, which should be, it's already passed, right? And then you have the autumnal equinox, which happens in summer. So those are here and here. Those are going to be the times when you get equal amounts of night and equal amounts of day. The other piece I left out of this is that the sun, along with the sphere of fixed stars, they all rotate together. Okay, so the idea is that the sun would still rotate once around the Earth to give the natural motion of the sun, where it rises once and then it sets and then it rises again the next day. So the sun basically travels around with the sphere of fixed stars, but it's also moving along this ecliptic right here. Now, in order to explain the days and nights variation, what you do is, for the northern hemisphere, this is the so he called these the tropics, this point and this point right here. They're the turning points. The word tropos means to turn. So they're called the turning points. So this point right here would be what we call the what are the names for them? The summer solstice in the northern hemisphere. It would be the winter solstice in the southern hemisphere. And then this point is the winter solstice. And if you don't know what those are, the summer solstice occurs basically on about June 22nd, and the winter solstice occurs on, what is it? It's December 21st, 22nd, something like that, right? And the equinoxes occur around the 22nd of March. And this would actually be, if I want to get this correct, this one would have to be 9/22. Okay, it's around there. It could be the 20th or the 21st. But the idea is that here's the sun, right? So here's summer. This is June 22nd right here. And then the next important, whatever event will be the equinox, which would be September 22nd. And then you go to the next thing, which is winter solstice, which is December 22nd. And then it repeats. On the backside over here, you'd have the spring equinox, basically. So this produces everything that you see. You learned about the winter and summer solstice in your art history class. Yeah, that makes sense. It's a pretty important, event across most societies throughout history, so. Okay, so these things will produce everything that you can observe to this day about the motion of the stars in the sun, okay? It explains everything. It explains what the sun does in the morning and the night. It rises in the east and sets in the west. And it will also explain the motion of the stars, right? So there's one thing left to describe, which is the planets. And before I get into that, I'm just going to stop and ask if anyone has any questions. Do you have any questions? Then I guess I should ask you, does this make sense? Does this seem like a reasonable way to describe the motion of the stars and the sun from an ancient perspective, where you think, they all think the Earth is sitting still? That's the important thing. Because they don't really have a reason, they don't have another reason to think they don't have a reason to think that it's moving through space, right? Which is kind of what you all learn when you start learning about the planets and stuff. But as far as they knew, the Earth's sitting still. Yeah, based on what they had available to try to understand, right? Okay. It's also a lot simpler to describe all these different motions if you just pick one thing to be still, right? If you just choose one thing that you're going to make still, you can describe all the other motions relative to it. Like, that's something that we learned about early on in this class when we were talking about relative motion, right? If I tell you that a car is moving down the road at 30 miles an hour relative to the ground, there could be another observer that's traveling alongside that car at the same speed, and they would say that car is traveling at rest relative to them, right? So all velocities are relative, including rotational motion. So when you're trying to describe the motion of all these different things, the simplest thing to do is to make one assumption, and that assumption was that the Earth is sitting still, and then you just describe everything else. Okay. That doesn't mean that Ptolemy believed all this stuff, because for Ptolemy it wasn't about believing in something, like what is true and what's not true. He was just a really good scientist, and he just wanted to be able to predict where these things were going to be, you know? That was it, really. It's like, how can I predict where the sun's going to be? How can I come up with a way of telling people, you know, what the sun is going to do on a day-to-day basis? Was a king that proved that though the sun revolved around him until Galileo proved him wrong. I guess you were trying to say that there was a king that thought the sun revolved around him until Galileo proved him wrong. I don't know specifically like who you're referring to, but that sounds like it's very possible. Yeah, I don't know. Okay, so let's talk about the planets. The planets are a lot harder to describe because if you look at what the planets do on a day-to-day basis, it looks pretty much like a star. So to the ancients, they would call these wandering stars. In fact, that's what the name planet means, pretty much. The word planao in Greek means to wander. So planets to them were just stars that were really, really bright, and they did not behave like the fixed stars, right? So to go back to the definition, these are what we call fixed stars. That is to say, they do not move relative to each other. Yes, they move every night, but they don't move relative to one another, so they're kind of fixed on this sphere. But planets wander. They don't stay in the same place, okay? Every night they undergo this motion of the once a day around in a circle, but on a day-to-day basis, they don't even do something as simple as what the sun does. They do something much more complicated. So if you were to watch a planet, let's say we look at the planet Venus, for example, and we plot over a year or so what it does. We basically we pick where Venus is. Let's say we pick a color that's kind of different. Let's say this is where we observe Venus in the sky. Okay. Maybe the sun's there, maybe we observe Venus over here, okay? And now we want to plot what Venus is going to do on a night-to-night basis. And what it's going to do is really strange. It basically will travel along a path that seems to be kind of straight, but then it will start to do things like loop around like this. It will basically like do these kind of curly cues throughout the night sky as we track it. And this is over multiple days, not over one night, but over multiple days, okay? So it will have this thing where it basically is going in one direction, but then it turns around and then it turns back around again. And then it's going in this direction, then it flips backwards, and then it comes back around again, and it kind of keeps going forward again. Okay? And it's moving. What you have to imagine for yourselves, I don't want to muck this up too much, but what you have to imagine for yourselves is that on a day-to-day basis, it's doing something like this throughout the sky. Okay? So what we're saying is that its location, what we're tracking, is its location relative to the other fixed stars, right? It's not fixed relative to the star, for example, because it's getting closer to it and then it's getting farther away from it, right? Okay, so that's what Venus would do. But again, everything does this. One time per day it goes around in a circle like this. We're just saying that on a night-to-night basis, as we keep looking at what Venus is doing, we see that it's kind of scooting across the sky like this. So in order to explain this, Ptolemy had to do something that was, I think it's pretty brilliant. So what he did was, he said, okay, let's just look at Venus and the Earth, okay? So the Earth is right here at the center. We're just going to use a dot to represent the Earth. And Venus is going to basically be traveling along in what we call an orbit these days around this path right here, okay? But because Venus can't simply do this. It can't just go around in a circle because that would not produce these kind of motions. So what you have to do, or what he chose to do, was to use something that's called an epicycle, which is basically a circle riding on a circle. So he said, suppose that Venus has two types of circular motion, okay? It's very important to mention one thing here. Uniform circular motion was believed by the ancient Greeks to be kind of perfect. This was kind of their... it was like their first law of astronomy, you might call it, I guess, if we're using modern language. They kind of believed that if you're going to describe what something is doing in space, they didn't even call it space, what something is doing in the heavens, it better follow some type of uniform circular motion. Because what they observe is they observe that the moon undergoes circular motion. It goes around in a circle around the Earth. Also, you can look at the moon or the sun and observe that they're perfect circles, right? Circles so perfect that you really couldn't even draw them that perfectly on a paper or in the sand as they might have done. And when you look at the kind of orbit of the sun around the Earth, it follows this path called the ecliptic, which is a circle. And if you look at what the stars are doing, they travel in a circle. So for them, uniform circular motion was like the guiding principle to define what planets do, basically. It's like they don't know why they do this, why they do this curlicue motion, but they know that it must be due to uniform circular motion, because this is like their overriding principle for what things in the heavens do. Okay? You can think about this like Newton's first law. Newton's first law tells us what objects do, right? Objects tend to travel in straight lines until they... Well, for them, this was like their first law. Things need to move in uniform circular motion. And if you do anything else, well, then you're like a heretic, basically. Okay, so back to Venus. Here's the Earth, here's one circle, and here's a second circle. So we have two circles, and we're going to use uniform circular motion to describe what Venus is going to do. So Venus is going to be sitting, like, for example, like right here. That's Venus, okay? And what's going to happen is that Venus is going to go around in uniform circular motion around this circle, and this circle is referred to as an epicycle. Okay, and it's almost like a gear wheel on top of a gear wheel when you see what it does. So the idea is that now Venus will go around this circle, but the epicycle itself will travel around the circle too. So after, for example, like a quarter cycle, the epicycle is going to be down here. Let me just copy paste this. After a quarter cycle, the epicycle is going to be like down here, and Venus will have been traveling as well. So Venus may now have moved, for example, to like right here. Okay. And so with that combination of a circle that goes like this, that's constantly moving, can you see how we used to play with these toys when I was a kid called spirographs? I don't know if they still sell those. Do you guys have spirographs? Is that something you all remember like seeing when you were kids? No response. I'm assuming you've never heard of a spirograph before. That's fine. So I won't try to use that as an explanation, but that's basically what this thing does. Can you imagine how this would work though, right? You're looking at this at Venus from Earth, right? And it's basically going around like this, the way that I'm... Oh, they still sew them. Okay, I'm not crazy. It totally is, yeah. But yeah, if you were to trace out what Venus is going to do, can you see that this is basically what it's going to do? It's going to go around in kind of this, like, basically, it's going to produce this kind of motion. Right? Okay, so that was his trick to explain why it is that, like, sometimes Venus is going forwards, right? Like these pieces right here, which would be like from here to here, from here to here. But then sometimes Venus goes backwards, right? If we continue this path and we look at what Venus is going to be doing at different points, right here and here and here, eventually Venus is going to be going up here as though it's going backwards in the sky, right? So if, let's see, if it's going this way, then it would probably end up down here. I don't know if I'm going to get it to where, but eventually it's going to end up somewhere like over here. I don't know. And it's going to be moving this way while the epicycle is going that way. And that's what's going to create these kind of curlicues, right? I was going to look at this before class, and I forgot to do it. I'm going to see if I still have it saved. This is a really nice thing that one of my students shared with me a while ago. I think I may have lost the link to it, though. I'll look for it during the break. Yeah, okay. Anyway, so that's Ptolemy's system, and he applied this idea to, like I said, he could explain the motions of the inner planets, which were Mercury and Venus, so he could explain the motion of Mercury, Venus, And then they also knew about the existence of Mars, Saturn, and Jupiter. And he was able to describe the motion of all of these, basically, by using his epicycles. And these were called the inner planets. These were called the outer planets. These were kind of a little bit different from each other. The way that he had to describe what the outer planets did was a little more complicated. But nonetheless, he could describe all the motion of all the things that they saw in the night sky by using these ideas. And there was a unifying principle, too, called uniform circumvention. So this is like... It's kind of like one of the first real scientific theories that existed was Ptolemy's system of the world, because other types of science that existed at that time were coming from Aristotle and were much more akin to philosophy than science. Because what Aristotle would do is kind of just think about the way the world was supposed to work and logically try to deduce what was the reason behind things. So he didn't really perform any experiments or anything like that. But what Ptolemy did was Ptolemy had all kinds of data to work with because for years and years, different astronomers had been plotting out exactly the location of each of these objects in terms of their like angles in the sky relative to the Earth. So he had a lot of data to work with, and he could produce a system, and it was a pretty good system. Okay, so that's Ptolemy, so after a very long time, so I didn't look up and write down when Ptolemy wrote because I just don't remember, but I'm gonna say it's something like 2500 BC, maybe 2000 BC. I don't really know. But this was the theory of not just the ancient Greeks, but the theory that the entirety of Western civilization used for a very long time until Copernicus comes along in like the 1200s, I believe. And this theory was also adopted as the kind of accepted theory of the Catholic Church as well. So this theory, the idea that the Earth is at the center, was the theory that everybody grew up understanding and believing for a very long time. Okay? And then Copernicus came along. Now, I want to kind of emphasize a couple of other things before we move on from Ptolemy, though. Ptolemy was really clever. And he kind of realized that even though the epicycles worked and could reproduce the appearances that he saw with the planets, you'll notice that at the center of these epicycles, there's really nothing there, right? It's just, it's a thing that's going on a circle. There's moments in Ptolemy where he actually hints that it would make a lot of sense for the sun to be at this location where this is happening here. So it's really fascinating that I think Ptolemy actually understood that his system was hinting at the idea that the Earth is not at the center and that in fact the sun is the thing at the center, but he didn't really have data to back it up. It was just more like it seems like it kind of fits when you put everything together. But he shied away from doing that. He focused primarily on just looking individually at each of the planets and seeing them as each of them as being a different problem to solve, basically. Okay, so Copernicus. Copernicus is, well, maybe you all can tell me, what is Copernicus kind of famous for? Is he someone that you learn about? Nicholas Copernicus? Have you ever heard that name? Absolutely no one has heard that before? Is it that obscure? Sorry, I didn't realize that. Anyone here heard of Copernicus before? If you did, you don't remember it? Okay. Haiti, you saying you... Okay, so some of you have heard of him. Okay. Well, what is he known for, then? Do you remember, Bran? Anyone that happens to remember his name? Your dad wanted to name you after him. That's pretty awesome. Would have been a good name. He wasn't exactly a philosopher. I guess he could have been called a natural philosopher, because that is what they were called at the time. But Copernicus was a scientist, basically, and he was concerned with exactly the same thing that Ptolemy was concerned with. He wanted to describe the motion of the planets. And so what did he do? Well, he said, we got to change something. We can't have the exact same theory. So let's try a new theory. And the new theory that he tried was, let's just say that it might be a little simpler, as I kind of hinted a second ago, to just place the sun at the center and then have each of the planets move in orbits around the sun that are circular. So Copernicus said that everything moves in circular orbits. This isn't even true. I can't say this. I used to think this was true, but then I read more about this. orbits with the sun at the center. That's the thing that he did. This is sometimes referred to, like when I learned about this in like, I don't know, 5th grade or something, this is referred to as the heliocentric theory. The idea that the sun is at the center of the universe as opposed to the geocentric theory where the Earth is at the center of the universe. Okay, so the heliocentric theory. So you put the sun at the center, and then you just have, this is, I mean, I would say this is kind of how you all learn how the cosmos works. You put Mercury moving around a circle around that, and then you put Venus moving around in a circle around that. He tried really hard to use circular orbits. I mean, when I grew up, I learned that it was circular orbits, but the reality is that circular orbits just will not work. So here's the Earth, and you just continue on. So you put the sun at the center, and now you create an actual system where you put all of the planets, and I'm not going to draw all the planets, but for them it would have just been 5 planets, right? So Mercury, Venus, Mars. So you'd have Mars, I'll just write these out here. You'd have Mars followed by Jupiter, followed by Saturn, and they would all have their own orbits, right? They go in a circle around here. Okay, so what Copernicus did that was kind of groundbreaking was he basically said, let's put everything together. Ptolemy was separating out a different theory for Mercury, Venus, Mars, Saturn. He had different rules to describe what they were doing, and Copernicus basically put them all together and put the sun at the center. Now, this was not a theory that was very well accepted because, as I said, the theory of Ptolemy had been around so long that it had been have been accepted by the Catholic Church as not just their theory of how the universe worked, but as dogma. Like, it was thought of as being heretical to describe anything other than the Earth as being at the center, because, I mean, that fits pretty well with, I think, Christian theology. I mean, I'm really overstepping my bounds here. I'm not trying to pretend I know anything about this, but if you think about, like, the Genesis story in the Bible, like, God created the heaven and the earth. Like, the idea is the Earth is a special place, right? And with the Earth being at the center of the universe, that's completely fitting with that Genesis story. Putting the sun at the center kind of didn't make people happy. So what Copernicus did was he figured out all the math you needed to make this work, and he actually waited to publish his material until he was on his deathbed or was dying or something like that. He had his estate make sure that they published what his results were and his findings and his mathematical theory to make all of this work, because it's not that simple. And then, yeah, so that's this. He is kind of the head of the heliocentric theory of the universe. Now, the interesting thing is, so Copernicus wanted to save one thing about the old theory. He wanted to get rid of the Earth at the center. He wanted to put the sun at the center, but he still wanted to save this piece, uniform circular motion. He thought if he could save that, that would be like a big win. Unfortunately, when you try to describe the motion of Mars and Jupiter and Saturn, trying to put them on perfect circles just does not work. It'll lead to predictions like Mars will be like, really far away from where it's supposed to be if you're trying to predict its location. And in order to make it work, what he had to do was he basically had to use the same thing that Ptolemy did. He used epicycles, except that his epicycles were even more complicated. In order to make this system work with the sun at the center, he had to put Mars on like 3 different epicycles as it revolved around. And he had to put Jupiter on like 2 different epicycles as it revolved around. So imagine, as complicated as it is to describe one epicycle going around this outer cycle right here. Imagine if you had 3 epicycles. So that would be like you have a circle, and then on that circle you have a circle, and on this circle you have another circle, and somehow on this circle you have another circle, and then you have the planet right here that's going around, and all of them are moving at the same time. Like, again, like a bunch of gear wheels, basically. So it's really complicated, and I'm definitely not going to go into any of the details about that, other than to say that there's something funky going on with Copernicus' theory, right? If you have to have a bunch of different mathematical tools and epicycles in order to make it so that you can have the sun at the center, well then maybe your theory isn't as good as you think it is, because it might work, but there's probably a simpler theory out there, basically, right, than this really complicated circles on circles on circles theory, right, which is what they were doing. You could think about it as they were basically just kind of using duct tape to fix their theory. That's what they were basically doing, right? They were using some kind of like ad hoc solution that worked, but Another thing to say about Copernicus that's really important is that he stole a lot of his mathematics. I don't know if stole is the right word, but I think it's the right word. He stole a lot of the ideas of his theory from Muslim astronomers. So like he spent a lot of time going to the Middle East and going to libraries and studying the work of Muslim astronomers, and then basically took their ideas and brought them back to the kind of Catholic Western Europe area. So he gets a lot of credit for stealing the work of other people, I guess you might say, and codifying it and bringing it to the West. So that's how we end up with the material over here. All right, so that's Copernicus' theory. Copernicus' theory has a lot of problems, though. So that's where we get to our more modern understanding, which is a guy named Kepler. Okay, so Johannes Kepler was also an astronomer, and he really... I left somebody out of this theory. Okay, Kepler's going to come, but he's next, actually. I forgot there's one more person. In between Copernicus and Kepler was a guy named Tycho Brahe. I'm probably mispronouncing it. It's kind of a weird name, though. Tycho Brahe. So Tycho Brahe was a wealthy, some type of an aristocrat. I think he was a duke of some type. This is somewhere in Europe. I want to say Poland, or, but I could be wrong. And he had access to an observatory where he basically took extremely precise astronomical data. So he took really precise data about the position of planets, and he basically just kind of codified all this. He wrote it down in all kinds of, on papers. And Brahe had basically one mission. His goal was basically to prove that Copernicus was right. Okay, so at this time, Copernicus' theory still wasn't very accepted. People would teach it, but it wasn't completely accepted throughout the West as the true explanation of what was happening. Ptolemy's theory still worked. This is important to understand, that if you have a theory that works really well, like Ptolemy's, it was extremely accurate. You could still use it to this day to predict the motion of planets and stuff like that. Then what's the point of coming up with a new theory if it doesn't add anything? Especially if it pisses people off by putting the sun at the center, right? By moving the Earth out to just being just another planet like all the rest of them, right? So Brahe was trying really hard to prove Copernicus right, but he couldn't do it. He had a lot of difficulties in fitting the motion of each of these planets to a circle, okay? Whether it looks like it or not, each of these paths here is a circle. It's just that the actual thing itself has to ride on epicycles. So Brahe couldn't do it. So Kepler is basically... I mean, you could say he was Brahe's assistant, but really Kepler was a scientist in his own right who pretty much had nefarious ideas. He wanted to basically steal all of this data that Brahe had, because Kepler thought he was a good enough mathematician that if he had all of this data, he could basically do what Brahe couldn't do, and either prove Copernicus right or come up with a better theory to replace Copernicus' theory, right? So Kepler takes the data from Brahe. In fact, I can't remember all the details of this, but if you read about this, it's kind of interesting because there were like lawsuits and things where Kepler was like battling. Like, I think Kepler took the data, and then the descendants of Brahe, like his children's and niece and nephews, tried to like sue Kepler to get the data back. It's really kind of, it's kind of funny to think about. But anyway, so Kepler has the data now, and he spends years, something like 5 to 10 years, trying to work out what Brahe couldn't do. He wanted to, again, prove that Copernicus was right, but Kepler figured out it was impossible, okay? And the problem that Kepler was dealing with was basically this. He said, suppose that I take the sun right here, and around the sun on a piece of paper, let's say that I look at the data that I have and I plot out the location of one of the planets. And let's say the planet we're looking at is Mars, okay? And what I'm going to do, not Mars, Mars. Let's say the planet I'm looking at is Mars. And what I notice is that Mars is here one day, and then maybe it's like here another day, and then it's here another day. And let's say it's over here, and then let's say it's over here, and let's say it's over here. Okay, so let's say we have 6 data points, and you want to fit the orbit of Mars onto those data points, right? And so what you do is you take a circle. Maybe at that time he would have taken like a compass or something like that. I don't really know. And you would basically try to find a way to fit a circle to all these data points. See if I can actually get a circle here. That looks kind of like a circle. And what you notice is, I I just drew these freehands. I don't know how well this is going to work, but it should work well enough to prove the point. What you notice is maybe you can get like 5 out of the 6 data points. Like maybe you say that's good enough. You know, maybe this one's a little bit off, but that's okay. But you notice there's like this one's way off, right? You can't actually get this one to fit on a circle. So you take your circle, maybe you shift it over, and you're like, well, maybe I just need to. Let's just try a different size circle. Okay, is there any way I can get? Oops. And maybe you can get like some of the data points, but every time he tried this, he basically couldn't get. It was impossible. Okay. So what Kepler realized is that there is no way that you can take the position of Mars and fit all of the data points on a single circle, okay? So you're going to need a different shape. And supposedly Kepler tried all types of different shapes, but if you actually just take these points that I picked here, and you just if you're willing to say, well, maybe it's not circles, maybe the ancient Greeks were wrong, then what you end up doing is you realize that the type of orbit that you need to make these things actually fit on the circle is an ellipse. So that leads us to Kepler's laws, because this is Kepler's first law. The first law says that planets orbit the sun in elliptical paths. Oops. With the sun at one focus of the ellipse. And I will say what I mean by this. So that's what Kepler figured out. Kepler figured out that if you don't care about uniform circular motion anymore, which again, this was the unifying principle for the ancient Greeks and for Copernicus. He wanted to keep circles. That all of a sudden it becomes a lot simpler. You just say this is the path of the planet. It undergoes this type of elliptical path like this. Now, when you're talking about an ellipse, let's draw another one over here. Let's use a different color. An ellipse has certain properties, okay? And to show what those properties are, what I'm going to do here is I'm going to try to draw a line straight through this ellipse like this. And then we'll draw another line straight from the top to bottom like this. And let's just talk about the properties of an ellipse so we can understand what the focus is, okay? So an ellipse is an object that is basically like a circle where you've kind of stretched it in one direction. A circle would have, this line would be the diameter of a circle, and this would be the other diameter, and they'd be equal to each other. In an ellipse, these lines are not equal to each other. We call this one the minor axis because it's short, and we call this one the major axis because it's long. Okay? And then we can put the sun into this picture now. The sun is going to be at one of the focuses of the ellipse. An ellipse has 2 different foci, one here and one over here. They're at very specific locations, but we call those the foci. So this is a focus, and this is a focus. And the way that an ellipse, one way in which you could define an ellipse is if you were to take a line and draw it from here to the edge, and then draw a line from that point to the other focus here, then these 2 line segments, when you add them together, will have some length. And no matter what point you pick on the ellipse, the lengths will be the same. The total length will be the same, basically. So if I take this line plus this line, it's going to have a certain length. And if I then pick some other random point, like let's say that I pick a point right here, if I draw a line from here to here and a line from here to here, okay, I picked a bad point because that looks like it formed a rectangle. Why is it not undoing? Undo. Undo, undo. Let's pick a different point. What if I pick like this point over here? Like here. If I pick that point and I now draw 2 new lines, which is different colors. So I draw a line from here to here. And then I draw a line from the other focus to that same point. The idea, I didn't mean to make like a triangle, that was just an accident. The idea would be that if I take this red line plus this red line, it's equal to this green line plus this green line. Okay? That's what the focus is. It basically tells you, like, if you were to draw a line up to a point and then back down to the other focus, that the sum of the lines will be the same. Okay? All right. So the sun is going to be located at one of these foci. So we'll just say that the sun is located here. So here's the sun. And then a planet would be somewhere along this path. So for example, the planet might be like, right here. That's my planet. Okay, so you need elliptical orbits to describe, the motion of planets, pretty much. Another couple things to define here before we move on are the major axis. We can cut it in half, and we can call this distance from here to here, which would normally be like a radius for a circle. So the quantity A is what we call the semi-major axis of the ellipse. So it's half of the major axis. That's where we get the name semi-major. And then we'll use the symbol B. So B will be this distance from here to here. And B will be the semi-minor axis. Okay. And then this is the center. Okay. All right. Does anyone have any questions? I guess the next thing to do would be to talk about eccentricity. So we can use the symbol E to represent eccentricity. Right now, we're mostly just talking about how ellipses work. How am I doing on time? Okay. The way that eccentricity works is it's a value. The value of E can basically go between 0 and 1. Okay. And eccentricity is a description of kind of how much the ellipse is different from a circle. Okay. If you have an eccentricity that's equal to 0, this corresponds to a circle. Because a circle is just a special case of an ellipse. So I'm going to put one more distance on here. So the distance between the focus and the center, I'm going to say, is equal to E times A, okay? So this distance between here and here is equal to E times A, okay? And it's also the same over here. EA will be this distance too, from here to this focus. It's symmetrical in that sense, okay? So can you see that if E is equal to 0, the distance between the focus and the center would be equal to what? If you make E equal to 0, then you get 0 times A, so the distance between the focus and the center would just be, it'd be 0, right? That would mean that the focus was on top of the ellipse, so you basically just get a circle. Basically just get a circle, okay? Anything between 0 and 1 is going to give you an ellipse. And if E is really big, right, think about what it does. E basically just tells you the distance from the center out to the focus, right? So let's say E was equal to 0.99. What would that look like? If E was equal to 0.99, that would be like a really, really skinny ellipse, like this. This would be a very, very high value of E right here, okay? And for this, we'd basically say the sun would be like way over here. So there's my sun. So this would be an example where E could be something on the order of like 0.9, for example. Maybe more, maybe 0.95 or something like that, right? So really high eccentricity means that you have an orbit. These are orbits, by the way. The planet would go around in a circle like this, right? Not circle, in an ellipse like this. It would orbit around. If you have an orbit like this, where the eccentricity is really, really, really high, then you're going to have a situation where you have an object, like this is what comets do, that may travel near the sun for some short amount of time, but then spend most of their time really far away from the sun until they eventually come back, okay? Because it turns out that Kepler's laws about how planets orbit the sun, it doesn't just apply to planets, it applies to asteroids, it applies to comets, it applies to satellites like the moon, it also applies to man-made satellites too. Anything that you put into orbit will automatically go into an elliptical orbit. And by doing different things that we'll learn about, you can change the orbit of your object. Okay, so does the idea of eccentricity make sense? Okay, Now, it turns out you can go to, if you go and look up, like we're gonna look at the moon and Mars, I think. I'm just gonna search for Mars, and we're gonna go to Wikipedia. And normally on Wikipedia, here it is. It shows you the eccentricity. So this is the eccentricity of Mars. It tells you other things too, like here's the semi-major axis that we just described, right? And if you mouse over, there's a picture of what an ellipse looks like that we just also drew, right? So I find the eccentricity to be the most kind of interesting thing to talk about. And again, you can go read more about eccentricity if you want to here as well. But this is the eccentricity of Mars. I'm going to put these kind of side by side here. So this is Mars. Oops, why did it do that? E, there we go. So this is for Mars, and I want to go and find what it is for the moon and for Earth, because it's very interesting when you look at the Earth and moon. So this is the moon. And then we're going to look at the Earth. And I guess we'll throw a comet in there too, just to get an idea. So where's the eccentricity? Here's the eccentricity for the Earth. This is very close to 0, you'll notice. In fact, all of these are pretty close to 0. This is for the Earth. This is around the Sun. And let's do one more thing. Halley's Comet. So, okay. This is what Halley's Comet is. 0.96. Does it do that? That's so weird. Okay, so do we need to do one more of these? These are probably fine. So when you look at these things, remember that E equals 0 is a circle, right? And E equal to 0.95 is like a really oblong things like this. So this orbit down here, let me make these digits a little bit more readable. There we go. You don't need so many digits for the Earth, right? We can just go out to like 3. So something I think is really kind of relevant when we look at these numbers right here. When you look at Mars, the Moon, and Earth, notice that their eccentricities are all about, well, for Mars is about 0.1, and for the Moon it's like 0.05, and for the Earth it's 0.01 or 0.02. So what does that mean about these orbits? That means that these orbits are very nearly circular orbits, right? But they're off by just a little bit. Even the Earth's orbit is, to a high degree of accuracy, you could say that the Earth's orbit around the Sun it's a circle, because this number is so close to 0, right? And I think when you look at these types of numbers like this, I think it makes a lot of sense why ancient astronomers thought that everything was moving in circles. It's because they pretty much are, to a certain degree of accuracy, right? Now Mars is like 0.1, so it's pretty far off from being a circle. But, it's still pretty close. And the Moon is the thing we have the most experience with because we see it every single day, and it's pretty close to being a circular motion. And the Earth, which means what Ptolemy would have observed as the motion of the Sun, it's also very close to being circular. But when you start to look at things like comets, you realize that, wow, this isn't even close to a circle, right? 0.96. Halley's Comet has a period of about 77 years, 80 years almost, which means that this comet only ever shows up every 80 years. It means that everyone in your lifetime will probably see the arrival of this comet once, maybe twice. The only way you'd see it twice is if you saw it when you were born, like within the first 10 years of your birth, and then, saw it right before you were about to die, right? Because most people don't live to be, people live long, but 80 years is a really long time, right? So this takes a really long time to even get near the Sun, and if they had more experience with stuff like this, they may have been more likely to realize that things were moving in ellipses instead of moving in circles. Anyway, so it took a really long time. Eventually people ditched the idea of circles and started using ellipses with Kepler. It doesn't mean people instantly accepted Kepler's ideas, but over time it became clear that Kepler's ideas were correct, and they were actually like the simplest idea. We'll take a break, but we're gonna talk about Kepler's 2 other laws that describe the motion of the planets. this describes kind of the track that the planets are moving along, these elliptical paths. Yeah. So does anyone have any questions before we take a break? All good? Okay. Alrighty. Well, take a break. We'll come back, and then we'll talk about Kepler's two other laws, and then we'll talk about how Newton described basically the cause behind these laws. So Kepler's laws are observational, and Newton's going to come up with kind of the how of how that works in terms of the things that we know about so far, which are forces, because we want to describe everything in terms of forces or interactions.